Okay, so hello everyone. In the last class, we did finite element discretization of weak form of the rod, and we only looked at the static part. Today we are going to look at the dynamic part of the weak form and how to linearize the dynamic part and further discretize the dynamic part. So we have finite element discretization of the linearized dynamic part of rod's weak form. Okay, so we have two things here: discretization and linearization. So we'll first do the linearization of the dynamic term. Linearization of the dynamic term. Okay, so if you write in an abstract sense, you have G, which is the total weak form, and that's G static plus G dynamic, right? And G statics, we have already studied how to linearize and further discretize. Linearization plus discretization have been worked out. And today we are going to look at the discretization and linearization of the dynamic term. And you might recall that this term is actually integral from 0 to L rho naught, which is the density of the rod, times the cross-sectional area A times R double dot, which is the acceleration of the center line. And this then gets dotted with del R, which is the variation in the center line variable, plus rho naught I omega whole dot, where I is the moment of area tensor. So I is the moment of area tensor. And omega is the angular velocity. Alright, so of course this has to be dotted with the variation in the rotation, that's del theta, and the whole thing is to be integrated. So we have ds also. So that's G dynamic, the weak form of the dynamic part of the rod equation. Okay? This I that you see here is moment of inertial tensor, as I told you. And as the rod rotates, this I also rotates, and this is actually given by R I naught R transpose. Alright? And omega is nothing but the axial of R dot R transpose. Okay. Now see, what's the problem really with the linearization? It's that when we wrote our total G, that G has to be written in terms of little r, comma, theta, and then your del r, del theta. And then we want to linearize this. So we'll say this would be equal to some G at some known state r naught, comma, theta naught, del r, del theta, plus its linearization, right? So it is not easy over d epsilon at epsilon equal to 0. And this will, when we linearize, we are perturbing little r and little theta, right? So little r, for example, this becomes r plus epsilon delta r. And theta is perturbed such that the rotation r epsilon is exponential of epsilon delta theta into r. So in that sense, this dV is actually a function of r, theta, then its increments delta r, delta theta, and also its variation del r, del theta. So that's how it was in the statics part. Okay. But now you see, we also have the acceleration, translational acceleration, angular velocity, and there is further another dot. So we actually have to write down the accelerations. We will need to write down accelerations in terms of these increments. Because basically we want that as we increment them, how does acceleration also gets implemented? That's what we want to do. So, okay, so that's our goal. So before going there, let's try to simplify this term over here. I omega dot. So I times omega whole dot. So that's R I naught R transpose, and this omega we can also write as R into omega naught. So omega naught is like the pullback of omega. So just as omega is defined as axial of r dot r transpose, omega naught is simply axial of r transpose r dot. And then you will show that omega naught and omega will be related. Omega naught and omega will be related in the following way. Omega equals omega naught. Okay? So let's come back here. So we have to take the dot of the whole thing. Now these two become identity. So this is actually R I naught omega naught whole dot, and then we take r dot. Okay, so this is r dot I naught omega naught plus r I naught omega naught dot, right? And then what we do a trick here. So we say that r dot will write as, so we can do the following. We pre-multiply by R into R transpose, and then we have R dot I naught omega naught, and plus this R I omega naught dot. Okay, and then you can see that we have this big R common in both of them, and this R transpose R dot is actually the skew symmetric of omega naught. So this simply becomes omega naught cross I naught omega naught, right? So this whole thing is rotation times omega naught cross I naught omega naught plus I naught into omega naught dot, and omega naught dot is actually the angular acceleration. Okay, so this is alpha naught dot. Omega dot is alpha dot, and omega naught dot is alpha naught dot. And you can also show that alpha and alpha naught are simply related through that rotation. Alpha equals big R times alpha naught. Okay? Alright, so let me erase the board. Okay, so if we use that, then your G dynamic, that becomes integral of rho naught A R double dot plus rho naught R I naught alpha naught plus omega naught cross I naught omega naught and then this gets dotted with okay, so I have this here, this has to be dotted with del R and this plus, and this gets dotted with del theta. Okay, and then the whole thing is then integrated in ds. So that's my G dynamic, the new form of G dynamic. So in dynamics, what happens? We would know everything at a time step n, and then we want to know all the things at a new time step. So at a given time step n, at time step n, we would be knowing small r of n, then big R of n. Then we will also be knowing the velocity v n, which is r dot, then omega n, or you can say omega naught of n, and then the acceleration a n and alpha n, or you say alpha naught. Okay, so these things are known to you, and you want to know the same thing at the next time step. So at time step n plus 1. So we want to find that. So coming back to this dynamic term here. So we are writing this at, let's say, time step n plus 1. So we want to get these things at n plus 1. Time step n we already know, and we want to get this now at n plus 1. So these are all at n plus 1, right? So we can also write this as acceleration a at n plus 1 dot del r plus rho naught r at n plus 1 into I naught alpha naught at n plus 1 plus omega naught n plus 1 cross I naught times omega naught at n plus 1. This is then logarithm of theta.
So alpha naught is the angular acceleration at time 0.
No, see, alpha naught n plus 1. So alpha is the angular acceleration.
Yes, sir.
So alpha n plus 1 is the angular acceleration at n plus 1. And what is alpha naught n plus 1? That's simply R transpose of alpha.
When we related alpha is r into alpha naught, but alpha naught
Yes.
was, what was that alpha?
So it's just a variable. So also, so that's a good question. Let me just do the side calculation for you. So we have omega and omega naught. Right? What is omega? Omega is the axial of r dot r transpose. And omega naught is the axial of r transpose r dot. Isn't it? So, and then omega dot. So what will be omega dot? Omega dot is by definition alpha. So alpha is your omega dot. What if I write this as r omega naught and whole thing dot? So what does this become? R dot omega naught plus r omega naught dot. Right? And see what is this? R dot omega naught. So R dot would be again going to plug in R transpose with R omega naught plus big R alpha naught. That's by definition. Omega naught dot, we are saying by definition is alpha naught. Okay? But look at this term. What is this term? R dot R transpose. That's skew symmetric of omega. And R times omega naught is also omega. So what does this become? So this is actually omega cross omega. So therefore this goes away. So what we see is that alpha is R times alpha.
So what is I naught?
Yes, so I naught is the moment of area tensor of the cross section. You know that like you have learned about IXX, IXY, IXZ, IXY, IYY, IYZ. So that's 3 by 3 matrix. So I naught is that. And I naught does not change with time.
It is at time
Because it is in the straight state. And as the cross section rotates, then the rotation, the inertia tensor is also going to rotate. Right? Okay. Alright, so coming back here again, you see now, if you remember, you had the static part also, and in the static part, when you linearize that, everything was in terms of little r, little theta, delta r, delta theta. Right? And we want to do the same thing over here. But unfortunately, we have acceleration here and angular velocity. So we want to write these two things in terms of delta r, delta theta, those increments. And to do that, you know, this is always done in any dynamic term. Whenever you have dynamics, we always do that. We replace these accelerations in terms of increments. So how to do that? Let's see. And for that we are going to use what's called Newmark scheme. So according to this scheme, so as you go from one time step to the next time step, let us define U as the change in R from one time step to next. Okay? And in this case, we are going from n to n plus 1. We are going basically from n to n plus 1. So U is nothing but R of n plus 1 minus R n. That's by definition. And in Newmark scheme, what we say is that the velocity at n plus 1 is given by velocity at n plus delta t. So it's a discretization scheme, delta t into 1 minus alpha times acceleration at n plus alpha times acceleration at n plus 1. You see, velocity at n plus 1 is Vn plus delta t times the weighted average of acceleration at nth and n plus 1 step. The forward Euler, that's explicit scheme. In that scheme, we say that Vn plus 1 is equal to Vn plus delta t into A. If you have an implicit scheme, then we say it is delta t into An plus 1. But this is the mixture of those two. You have this alpha. If you make alpha equal to 0, it becomes explicit. If you make alpha equal to 1, it becomes fully implicit. And for any other value, there is Newmark scheme. Similarly, for the displacement, we say this is equal to delta t into Vn plus delta t square times 1/2 minus beta into An plus beta times An plus 1. Okay, so you see what is this? So displacement is equal to Vt. What's the simple thing that we have learned? Acceleration is constant, then displacement is equal to Vt plus half At square, right? So here we have delta t into acceleration by 2. If you set beta equal to 0, then that's what you get. But in the Newmark scheme, we take the mixture of the two accelerations. So we take weighted average of the two accelerations. And it turns out this scheme is stable. There is some stability issues whenever you discretize. And this is in a stable scheme. So the choice of alpha and beta can decide whether your scheme will be stable or unstable. Anyway, so this is the discretization. Now you see this discretization. Using this discretization, you get U. But what we want to do is the reverse. I want to write down acceleration at n plus 1 in terms of everything at the nth step and the U. Increments के terms में लिखना चाहते हैं. So how can we do that? No, it's quite simple. Just look at this term. Bring everything on the left hand side and just skip this. Then you have acceleration at n plus 1. In terms of acceleration at n, velocity at n, and the increment, isn't it? So we are going to use that Newmark scheme and we write then that acceleration at n plus 1 is equal to u over beta times delta t square. Right? Because you see we have this beta and delta t square. So if I divide by them, we get this here. Minus Vn over beta delta t plus 1 minus 1 over 2 beta En. Okay, so acceleration at n plus 1, now you are able to write that in terms of the things at nth step which are known plus this increment which is unknown. So you can substitute this formula for an plus 1 back here in the weak form over here. And when you do that, you get rid of acceleration and you write it in terms of u, the increment. Because that's what was there in the static part also. And we have to do the same thing also for alpha naught and omega naught. Okay? So let's see how we will do that. So let's go to this. So, now as we have rotation at n and we have to get to rotation at n plus 1. And we'll say that the increment in the rotation will denote that by zeta. Okay, zeta. So that implies rotation at n plus 1 actually exponential of zeta, alright, times rotation at n. And the same thing we could also write as rotation at n multiplied by exponential of some zeta naught. Okay. And how are zeta and zeta naught related to each other? You can again show that zeta is actually r zeta naught r transpose, and the zeta vector would be big R times zeta. But they show that quite easily. Alright? So, why did we come here? Because we want to write we will say this as the increment in rotation, zeta naught. So first increment by zeta naught, get the rotation, and then pre-multiply by rotation Rn to get your rotation at n plus 1. Okay? So basically we want to apply our Newmark scheme such that this u is the analog of zeta naught, then Vn would be the analog of omega naught, and An would be the analog of alpha naught. You see, this is in the translational domain. We want to do the same thing in the rotational domain. Okay? So basically, so now you can write that your alpha naught, let's do the increment. So zeta naught is than delta t times omega naught n plus delta t square into 1/2 minus beta times alpha naught at n plus beta times alpha naught at n plus 1. See, this is exactly what we have over there, isn't it? Look at this expression. And similarly, you can think of increment in angular velocity. So omega naught n plus 1. So that's going to be equal to omega naught at n plus delta t into 1 minus alpha times alpha naught of n plus alpha times alpha naught of n plus 1. See, don't confuse this alpha with this alpha. This is a scalar alpha, where this is a vector alpha. Okay? This alpha and beta are the parameters of the Newmark scheme, where this alpha vector is the angular acceleration. Alright, so with this Newmark scheme, we then want to write down our angular acceleration at n plus 1 in terms of everything known and the increment in rotation, theta naught. So how do we do that? We will have again this x exactly the same thing. That means alpha naught at n plus 1 is that equal to theta naught over beta delta t square minus omega naught at n over beta delta t plus 1 minus 1 over 2 beta times alpha naught of n. Okay, so that's for the angular acceleration, but we have angular velocity also with in the wave form, right? Omega naught at n plus 1 was also there, so you have to also write that. See, once you get your alpha naught at n plus 1, you substitute that over here, and then you have also formula for omega naught at n plus 1. So that means omega naught at n plus 1 is that equal to 1 minus alpha over beta times omega naught at n plus alpha over beta delta t times zeta naught plus 1 minus alpha over 2 beta times delta t times alpha naught at n. Okay, so we are able to write down both angular acceleration and angular velocity at n plus 1 in terms of the things at time step n and the increment. You see, this increment is here. Increment in rotation. But then the next thing we like to do is, this increment is of chi naught. Okay, why don't I write that in terms of zeta? Okay, this is zeta naught. Let's write that in terms of zeta. Okay, we can do that, right? So we simply use this formula, and then we have. So this becomes, maybe I should erase what we have over here. alpha naught at n plus 1 equal to r. What should that be? Zeta naught. How are zeta and zeta naught related to each other? Should we have r and n or r and n plus 1? R and n, right? As you can see here, this is n. So that's also n. And this is supposed to be r of n transpose into zeta divided by beta delta t square minus omega naught at n over beta delta t plus 1 minus 1 over 2 beta into alpha naught at n. And again for omega naught, we have omega naught at n plus 1 equal to 1 minus alpha over beta times omega naught at n plus alpha over beta delta t times r n transpose of zeta plus 1 minus alpha over 2 beta times delta t into alpha naught n. Okay, so now I have angular acceleration and angular velocity at n plus 1 in terms of this increment zeta. Alright, so what will be the next step then? Yeah? Substitute this, right, in the weak form and get rid of angular acceleration, angular velocity, and linear acceleration from there. Okay, so let's do that. So my G dynamic then becomes integral rho naught e times acceleration at n plus 1, and that would be u divided by beta delta t square minus omega naught of n over, sorry, this is not omega naught, this will be v naught over beta delta t plus 1 minus 1 over 2 beta into acceleration at n. So this is your acceleration at n plus 1. So we then dot this with del r, right? Plus, plus then you have to do that thing. Same thing for the rotational part, right? Dot, sorry, into ds. So now we have our dynamic wave form in terms of the increments u and zeta. So the next thing is to linearize this, right?
So that is V, not V1.
That is what?
V, not V naught.
Right, this is just V. So u is the only unknown here, right? So how do we linearize this? So u has to be perturbed, right? So earlier, what would you do? When you had r, you would say r plus epsilon delta r, right? So here also, u will change to plus epsilon delta r. Okay, u will change to u plus epsilon delta r. And then when you do d by d epsilon, you just get delta r. Okay, so the linearization of this term is quite easy. Linearization is simply rho naught a delta r over beta delta t square. Because all the things are constant, they do not change as you change your epsilon. Because you are only going to change the unknown, right? U is the unknown. So you are just going to change that by epsilon. And that's what you get. Right? So we do d by d epsilon at epsilon equal to 0. This term gives us this. And this has to, of course, dotted with del r. So, of course, this part was quite easy, but the next one is tricky.
This perturbation was a fixed time. Because we are, when in the weak form, we are dealing with spatial coordinates.
Yes.
So we have to fix the time at.
No, now actually, it's no more a time problem. You see, what are the unknowns? The unknowns are u and their rotation theta.
Yes.
So after solving this, you will get u and theta, which will lead you to n plus 1 times step.
This u is defined for nth time step between n to n plus 1.
Yeah, this is between n to n plus 1.
So when we are perturbing this u, we have to fix the time. We have to. When we say that.
Yeah, of course, when you are perturbing the u, you just perturb u, you don't perturb the state. That's always the case. Whenever you linearize, then you increment, but the state about which you are linearizing, that you don't change. Right? So we are linearizing this about the nth times, about the configuration in the nth times. The next thing is really, really tricky. Let's look at one of them, the acceleration. Okay, why don't I write the whole thing? So we have rho naught r I omega naught, sorry, I alpha naught at n plus 1. This one is at n plus 1. Plus omega naught at n plus 1 cross I naught times omega naught at n plus 1 dot del theta. Do you guys remember what did you have in the static part? In the static part, the rotation, how was that perturbed? The rotation was given by the theta, axial vector was theta, right? And theta, so the r of epsilon, what was r of epsilon in the static part? It was exponential of epsilon delta theta into r, right? Which actually is exponential of theta. Here comes the problem actually, because in the static part, the perturbation that you have here, delta theta, this is not the same as the perturbation that we have here, theta. why they are not the same?
This is the.
So let me try now. The perturbation or increment delta theta and zeta do not have the same meaning. And why is that so?
Perturbation in zeta is itself a perturbation between n to n plus 1 and then
Theta is between n to n plus 1.
it is a very small quantity and we are perturbating that itself. Theta is the perturbation in the angle theta which has been जो अभी तक आया हुआ थीटा उसमें थोड़ा सा
उसमें थोड़ा सा है
ये तो itself n से n plus 1 की छोटी क्वांटिटी को perturbation
maybe to see that, we have to see how will the numerical scheme actually evolve. So we would know thing at nth time step और n plus 1 में जाने के लिए उसके बीच में वो बहुत सारा इंक्रीमेंट्स करेगा, राइट? उसके बीच में काफी इंक्रीमेंट्स करेगा. Let's denote that increment by k, क्योंकि n तो टाइम का इंक्रीमेंट है. टाइम के इंक्रीमेंट का बात नहीं कर रहे, तो हम लोग n से n plus 1 में जाने के लिए बस सोच रहे हैं. n plus 1 से n plus 2 का भूल जाओ. तो n से n plus 1 में जाने के लिए जो प्रॉब्लम सॉल्व कर रहे हैं उसमें जो इंक्रीमेंट होगा, let's denote that by k. So now what is the meaning of zeta and what is the meaning of delta theta? डेल्टा थीटा क्या मीनिंग होता था जब वो इंक्रीमेंट होता था? इटरेशन
for the
न्यूटन इटरेशन, राइट. तो यहाँ जो इटरेशन चल रहा है वो k में चल रहा है, n से n plus 1 टाइम स्टेप में जाने के लिए k का इटरेशन हो रहा है. सो उस इटरेशन के दौरान लेट्स सपोज your rotation becomes r of nk. That's the rotation. R of n comma k, meaning this is the rotation at the kth iteration, which will actually be exponential exponential zeta at k times rotation at n. If let's say I am already at n comma k and I want to go to n comma k plus 1, then r of n comma k plus 1 will be exponential of delta theta into r of n comma k. So that was the meaning of delta theta. So during the iteration, as you go from one iteration to the other of the Newton-Raphson scheme, delta theta was that delta theta during the iteration with the jump that you had, and that was with respect to the previous value of the iteration. Okay, whereas this zeta that you see here, this zeta is the increment from the previous time step to the next time step. So this zeta is always from Rn. This is always from Rn. Whereas this delta theta is from Rn comma k. I hope you guys are getting this.
So how is this theta and delta theta will be related? Can we directly sum them or?
Yeah, that's a good question. And that's something we'll figure out. But before that, we have to realize whether they are different or not. Have you guys understood that they are different? See, this delta theta is during the Newton-Raphson scheme. As you go from one iteration to the other, that's what it was in the statics. So that's how this is defined. But this zeta of k, this is like the accumulated rotation, total accumulated rotation from Rn to the current value of iteration, to the current value of iteration. It's like a compound rotation. So you are, let's say, at Rn, and you have to reach Rn plus 1. Then when you do your Newton-Raphson scheme, you go from here to here, then here, and here, and here. Then these are your delta theta between two iterations. Whereas this zeta is the compound increment that's from here to here. The total accumulated. So this zeta, because this is with respect to Rn, and this has to then give you the current value of the rotation. So this is actually compound rotation. But the problem is, we wrote down these things, alpha naught n plus 1, for example, in terms of zeta. We haven't written in terms of delta beta. Okay, so let's say we are at the kth iteration of the Newton-Raphson scheme. So at that iteration, we have to again linearize, get the stiffness matrix. So at the kth step, when you linearize, then what are you going to write? The linearizing at the kth step, let's think of that. Which will lead you to k plus 1 step, right? If you are not understanding, please ask me. So that's how the lecture will become more clear. So let's think of linearization. Think of linearization at kth iteration. To get to k plus 1. Okay, so basically, so your R of n comma k plus 1 is then exponential of zeta k plus 1 times Rn. This we know. And then R of n comma k is exponential zeta of k into Rn. This also we know. And similarly, we also know that R of n comma k plus 1 is actually exponential of delta theta into R at n comma k. linearization purpose, you have to bring in that epsilon, right? So we will say that R of n comma k comma epsilon. So this means your perturbation from n comma k. So the meaning of this is perturbation from n comma k. Perturbation at the nth time step and during the kth iteration, right? And then we are doing this exercise.
This is updated Lagrange kind of updated and total Lagrange formulation.
Updated Lagrange. That's the difference. It's just an accumulated rotation. Anyways, this would then be, how will I do this? This is exponential of zeta of k comma epsilon. See, that's what it is. That's a perturbed zeta. The perturbed zeta at the kth step. Kth step पे perturb करने के बाद जो zeta है वो into Rn, and this should be equal to exponential of epsilon delta theta that we have done in statics into R n comma k. That's what we have. And then you simply do d by d epsilon. Right? So you can do d by d epsilon at epsilon equal to 0. So we'll have from there d by d epsilon of exponential of zeta k comma epsilon into Rn is equal to d by d epsilon of this thing. Do you know what is that?
What is the delta theta 0?
Yes?
Delta theta or 0 to
Exactly. So delta theta. That's delta theta. Into R and K. And R and K is simply exponential of zeta k times Rn. Isn't it? By definition, let you see there, and these two go away. Right? And when you do this, so we have to, of course, evaluate this at epsilon equal to 0. And this is going to give me something times delta zeta k. So this would be like the linearization of this zeta k comma epsilon. No, when you evaluate this at epsilon equal to 0, so basically you can say that zeta of k comma epsilon is actually zeta of k plus epsilon delta zeta at k. Okay? Of course, we don't know what you get here, what is that something. But this times delta theta k is equal to delta theta skew symmetric, which you can say as minus of exponential of zeta of k times delta theta. Can you see that? Because this delta theta cross, or maybe not, because this is also a rotation. It's not a vector. So let's just keep it as it is. But the bottom line is that from here we can get delta zeta k, the increment in the compound rotation. No, the increment in the compound rotation in terms of the increment delta theta. And it turns out to be equal to some operator t of zeta k into delta theta. And what is that t? So that Simo has derived in this paper, of course. It turns out this t is equal to as follows: E tensor product E plus the magnitude of zeta k divided by 2 over tangent of zeta k divided by 2 times identity minus E tensor product E minus zeta k is skew symmetric over 2. Okay? And this E is then the unit vector of zeta. Zeta k divided by magnitude of zeta. Okay, so that's how you relate your delta theta to increment in delta theta k. So let's get back to our rotational part of the weak form. Some of you will have to help me. But we are almost there. So isn't that R and n plus 1 into I naught alpha naught n plus 1 plus omega naught n plus 1 cross I naught alpha naught n plus 1. This is then called delta theta. Okay, so let's just look at this term, for example, this alpha naught n plus 1. So alpha naught, see, when you would have gotten this at some step n comma k, फिर वहां पर इसको linearize करना है, right? So alpha naught n plus 1, what would that be equal to? Alpha naught n plus 1 will write it as alpha naught n comma k. Anyway, let's write alpha naught at n plus 1. So that's equal to, can someone tell me what was that? Rn transpose zeta
zeta of n, zeta by beta delta t square
beta delta t square minus
omega naught n
by
beta delta t
plus
1 minus 1 by 2 beta whole into alpha naught n.
is that it? Okay, so this is alpha naught n plus 1. Now, during our iteration, you have gotten thing at n comma k, and then we want to linearize it at the step n comma k. So we have to think of writing alpha naught n comma k comma epsilon.
So that is omega naught n plus 1 about.
Because omega naught.
What's the I know omega naught n plus 1.
Oh, here, right. Okay, so now this expression at n comma k comma epsilon, what is that? That's simply Rn transpose of zeta of k comma epsilon, zeta of k comma epsilon over beta delta t square minus omega naught at n over beta delta t plus 1 minus half beta into alpha naught n. So now we have to linearize this thing. So that means d by d epsilon of alpha naught at n comma k comma epsilon at epsilon equal to 0. What is that equal to? You see, this is constant. This does not change to the epsilon. The epsilon changes only here. So this is not there, this is not there. It only comes from here. Even this is Rn transpose. This is not changing with the epsilon. So what we get here, and you also see that zeta k comma epsilon zeta k plus epsilon delta delta k. Right? So that means this simply becomes Rn transpose delta zeta k over beta delta t square, which is also equal to, after you use this thing, Rn transpose into t of zeta k into delta theta over beta delta t square. So that's the linearization. Now you have linearized this thing in terms of delta theta. That's what we wanted. Because when you compute a stiffness matrix, go for discretization, you are discretizing delta theta. So now we can do that expression, right? We can discretize delta theta and assemble this in the stiffness matrix. Now this was just one part. We just looked at this part, isn't it? Similarly, we also look at this part, but this is, I don't really have to do it. You guys can do it, right? Let me just show you how to do linearization of omega naught and this. So we will have to look at omega naught of n comma k comma epsilon. Right? So that's equal to, can someone tell me what is that? One minus alpha by beta omega naught.
Plus alpha by beta.
Is this omega naught of n? Okay.
Alpha by beta
Alpha by beta
by 1 by delta. In the numerator delta.
delta t.
Sorry, in the
Denominator, okay.
into zeta naught
beta will be at k comma epsilon, right? Plus
1 minus
1 minus
alpha by 2 beta
alpha by 2 beta
into delta t
into delta t
alpha naught n.
alpha naught n. Okay. Alright, that's omega naught n comma k comma epsilon. And as you see here, it's only this thing is changing epsilon. So all will go away. That means d omega naught n comma k comma epsilon over d epsilon at epsilon equal to 0 is simply alpha over beta delta t r n transpose, and then linearization of this, which is delta zeta, which we can again write as alpha over beta delta t r n transpose times t, operator t, of zeta k into delta theta. So we have also linearized this in terms of delta theta. Right? So that's what you have to do here one by one. See, in this term, in the whole term, you first linearize this one. So this would be r of n comma k comma epsilon. Linearization of this is quite easy. It's simply delta theta times r of n comma k. Linearizing this is saying will give you delta theta times r n comma k. So when you linearize this, you leave it as it is. Then product rule, leave it as it is, multiplied by linearization of this. When you linearize this, you do the first thing here, you get what you have over there. Then you linearize the second term, right? So you're going to use that. So after linearization, you have everything in terms of delta r and delta theta. And also you have the same thing from the statics part. Right? So that's why you get the linearization of dynamic term and also the statics term. Once that is done, then you have to discretize it, which you guys can do, right? Okay? So I think this one can you now work on the dynamics? Yes? Right. You should be able to do it now. Alright, so I think I will stop here then.